Okay, guys, we are picking up in our water notes. So this is water part two or part B. I'm not sure how I started that. But we're going to continue on, look at the last two properties that exist in water because water molecules are polar and because they can form hydrogen bonds with neighboring water molecules and also with other substances. So our next property is the property that the water is a quote universal solvent, and I kind of air quote that because as we will see, it cannot dissolve everything. It is not truly universal, but it does dissolve a lot of stuff. So a quick vocab review, probably a flashback to 6th or 7th grade science. We need to make sure that we understand all of the words in this picture. So first, a solution. This entire mix here in the beaker is a solution. So that is a mixture, a uniform mixture of two or more substances. In this case, specifically, you have a solute that is being dissolved and you have a solvent that does the dissolving. So our connection here to water is that water is the universal solvent. It really can dissolve most things. And so we'll kind of address that and talk about that as we move forward. But hang on to those vocab words, probably a review from previous, while I perhaps introduce you to some new vocab words that are associated with this property. So example, in a saltwater solution, if we have a saltwater solution in a beaker, the salt would be the solute and the water would be the solvent in the solution. Here are a couple of perhaps new words. So we're still in the vocab review section. I know it's not terribly a large section, so if you printed these notes, write small. You have 3 more vocab words. The term hydrophobic. So many of you perhaps can hear this ending phobic, and you can think of a phobia, a fear. So hydrophobic substances are water-fearing substances or water-fearing molecules. They are hydrophobic because they are non-polar molecules. And so let's tuck that away in our brain. We'll come back to it in a couple of minutes, that non-polar molecules are not interested in mixing with water. So you can see in this picture over here of hydrophobic, you have the entire sphere of the water on top of whatever this hydrophobic substance is, because there are no hydrogen bonds attracting it back down here to the hydrophobic substance. Hydrophilic is, on the other hand, water loving. And so water loving molecules that are themselves polar or fully charged. We call them ions, right? Positive and negative ions, cations and anions. Those would be molecules that are hydrophilic. And so here is a hydrophilic substance, a polar substance or an ionic substance. And here is that water that really enjoys bonding with, mingling with the substance. So you can see it's adhering, right? So our property of adhesion with water, with hydrogen bonds forming to another non-water substance. So hydrophilic things enjoy interacting with, bonding with water. Hydrophobic things do not. And there's one more word that I'll introduce you to, an amphipathic, in this case, molecule. So this is a molecule that has both polar and non-polar regions on it. So there is a polar region that is hydrophobic, right? Because polar things are there is a polar region that is hydrophilic because polar things are hydrophilic. So in this case, we're looking at a soap molecule that has a hydrophilic polar water-loving head. And then it also has a hydrophobic region. So a region that is full of non-polar molecules or bonds that make it repel the water or fearful of the water. And so soap is able to do a lot of what it does because it is an amphipathic molecule. Now, I'm hoping that maybe in 8th grade, you all learned a little bit about the cell membrane. And in learning about the cell membrane, you learned about something that looked kind of like this, but probably had a second tail. So these are the phospholipids from your cell membrane. They too are amphipathic molecules, which are critical in how they are arranged in a cell membrane to create a boundary between the outside of the cell and the environment that the cell exists in, and then the inside world of the cell. And so amphipathic molecules will come back up again in later units, but just be aware that this term refers to a molecule that has some part of it that's polar or hydrophilic and some part of it that is nonpolar and hydrophobic. And so if you think about if a water molecule were to be attracted to any part of this amphipathic molecule, what would it be attracted to? The hydrophilic polar side right here. Okay. So let's continue on in this function. We've got basic vocab down. What does it mean to be a universal solvent, right? That's what we have said. Water is a universal solvent. So what does that really mean? Well, it means that because water is a polar molecule, remember it has a positive and a negative end, it can actually tug on and pull apart any other molecule with a charge. So anything that is also polar or a fully ionized molecule. If the because the beauty of the water molecule, the polar water molecule, it's got the best of both. It has a positive end and it has a negative end. So as long as the substance that you're trying to dissolve has some sort of charge on it, you can attract some part of the water molecule to it. So if your substance is negatively charged, don't worry, the water molecule has positive hydrogen ends that will attract to it. If your substance is positively charged, your water molecule has a negative oxygen end that will attract to it. And so piece by piece, and we can see this really well up here in this diagram, here are the water molecules. This is a salt crystal, so sodium and chlorine. Sodium is positively charged and chlorine is negatively charged. It's an ionic, salt is an ionic compound. So when water starts interacting here, the different regions of the water molecules will be attracted to these different charged molecules in the salt and will slowly and surely pull it apart. So look here at the water mixing in with the positive and negative sodium and chlorine. Notice if we follow this arrow up here, notice that the chlorine ions in the salt, which are negatively charged, are forming attractions with the hydrogen, the positive ends in the water molecule. And so we see water surround salt, or we see water surround the chlorine with the hydrogen ends attracted to the chlorine because positives attract to negatives. But down here, it's the reverse because sodium is a positively charged molecule. So we see the oxygen end attracted. And that's a great pause in thinking about an application question that could be asked. If this purple dot were not labeled as a positive sodium ion, I could ask you, what do you predict is the charge of the ion here in purple? And you would have to know, because the negative oxygen ends are attracted to this purple circle, that purple circle must be positive. And so a quick check on sort of an application question to the fact that water is polar and can bond to positive and negative things as well as other polar molecules would be a question like that. So essentially, as long as a substance has some kind of charge on it, it could be a full charge, meaning that it's a positive or negative ion, like the salt compound, Or it could be a molecule that's polar like water with just slightly positive and negative charges. As long as there is some kind of charge, water is going to orient itself in an appropriate way, attract a positive or a negative molecule using the hydrogen or the oxygen, depending on what it's trying to attract. And then slowly but surely, it will pull that substance apart, which means it will dissolve it. So the salt up here is really pulled apart piece by piece by piece because of the water. Now, here is an animation of that process illustrated so we can see it a little bit more. So we see how salt dissolves in water, and it doesn't have volume, I believe, so it's just me narrating. So here's our water molecule, 1 oxygen, 2 hydrogens, and here's our salt crystal. So again, we have sodium and chlorine, and the water or multiple water molecules are going to dissolve it. Oxygen end is negative, hydrogen ends are positive, so let's watch it work. In the salt, the sodium is positive. So because the sodium is positive, the negative oxygen end will attract to it and carry it away. That one's chlorine. That was the negative chlorine ion. And so we saw the positive hydrogen feet attracted to it, carrying it away. So let's see. Here goes sodium. See you later. There goes the sodium, pulled away by the negative end of the water. And so over time, water will eventually dissolve because it was charged. Water could grab onto it. It would dissolve the overall molecule. Okay, so let's, excuse me, let's go back here. Oh, you wanted to freeze on me. There we go. And let's talk about this last section of why does this happen? Well, we discussed the charges, right? Because there are positive and negative charges both on a water molecule. It can attract to pretty much everything. What I want to introduce you to is this word called hydration shells. So hydration shells are what we call water surrounding a particular molecule or atom. So these hydration shells will form, they will surround the molecule, and they will pull the overall substance apart piece by piece by piece. Now, in your section of notes, you have a little more space, and I would like for you to add this next thing. I would like for you to add at the bottom that although water is called a universal solvent, it cannot dissolve everything. It can only dissolve something that has a charge or a partial charge, meaning it can only dissolve something that is ionic or is polar. But what happens if we encounter a non-polar molecule? So this would be something that is covalently bonded, and the electronegativities of the atoms in the molecule are the same. And so as a result, there is no unequal distribution of the electron anywhere around the molecule. There's no charge built up anywhere around the molecule. Water has nothing to attract to if there's no charge or partial charge. So water is a universal solvent, except for when it comes to nonpolar molecules. So nonpolar molecules are those hydrophobic things, fats, oils, waxes even. So think about just in everyday life, you know what happens if you were to take vegetable oil and pour it into a cup of water. At first, it would look like it's mixing, but then notice the oil, which is nonpolar, sticks with the other oil molecules and separates itself out. And that's really what we are seeing up here in this picture. Over here, the red dots are polar or ionic molecules. And so you can see water gets all the way around and clusters all the way around and starts the dissolving process. Over here, these red circles are nonpolar. And so the first thing to notice is that nonpolar molecules are actually attracted to each other. And so they clump together and they hang out together. And once they are together, the water cannot fully surround them. And so the water cannot dissolve them. So water is a universal solvent, except for substances that are hydrophobic or non-polar. Great examples: oils, waxes, fats, things that are called lipids, if you've heard of lipids before. Let's check out our last property. So our last property deals with a couple of different characteristics of a molecule, specifically water. But all of these characteristics kind of roll into a collective emergent property called moderator of water is a good moderator of temperature. So a moderator of temperature means really that water maintains a pretty steady temperature. It doesn't heat up terribly fast. And once it is heated, it maintains its temperature. So it doesn't cool down very fast either. So being a good moderator of temperature really comes from two properties that water has: specific heat, and then something called heat of vaporization. So let's talk specific heat first. Specific heat is a property of lots and lots and lots of molecules. It is not exclusive to water. So alcohol has a specific heat, mercury has a specific heat. This is not specific to water. But specific heat is defined the amount of heat, which is energy, needed to change the temperature of that substance 1 degree Celsius, specifically 1 gram of that substance 1 degree Celsius. So this is how much heat does it take to change the temperature of something. And for us, what we need to know is that water actually has a really high specific heat, which means it takes a whole lot of heat energy to alter its temperature. It's very, very slow to heat up. And that is because of the hydrogen bonds. So water will absorb a lot of heat energy in its hydrogen bonds before it actually starts to change temperatures. And that is a great thing. I'll give you an example of how and where we see this. I am sure, let's go with this top picture first. I'm sure if you've been to the beach, you know that there is a very big temperature difference between the temperature of the sand and the temperature of the actual ocean. So think in your head, which one is hotter? They've both been sitting there the same amount of time, exposed to the same amount of heat energy from the sun. But you start walking on that sand at noon, it is hot. It has had all day to absorb that heat. And because sand actually has a low specific heat, as it absorbed the heat from the sun throughout the day, it changed its temperature really, really rapidly. But then you make it all the way down the beach to the water, and you know that the water is not near as hot as the sand, even though they were both exposed to the sun for the same amount of time that day. That's because water has a high specific heat. Water will absorb that heat energy from the sun throughout the day and absorb it into its hydrogen bonds and actually resist changing the temperature of the overall body of water, or change it more slowly. And that is why we see the second picture down here. Because water has a high specific heat, we see that coastal regions, so think about where beaches exist, coastal regions actually have a pretty moderate temperature throughout the year. So in the summer, when it's really, really, really seemingly hot, the water will absorb a lot of that heat energy, and then it will give that heat energy back out to the land when temperatures start to, when seasons start to shift, and we start to see things like fall and even winter, they're not as cold as places that aren't near a giant body of water that's holding this heat energy stored in those hydrogen bonds. So in the summer, these coastal climates are pretty moderate because the water, the ocean, absorbs a lot of that heat energy. And then in the winter, these coastal climates are pretty moderate as well. They're not crazy, crazy, crazy cold because the water gives back that heat energy to the land. So staying near a large body of water like the ocean can be beneficial in maintaining your temperatures. Now you get too far north and you start dealing with other aspects of climate, but down here you can see it's pretty warm all year round, right? So not major drastic shifts in temperature between seasons annually, and that is because water has a high specific heat. So that's one way that water acts as a moderator of temperature. It keeps things around it pretty stable when it comes to temp. Water also has something called heat of vaporization. This is another property that lots of molecules have, but essentially, this is how much heat is needed to change the phase of water or a substance from a liquid form to a gas form. So that is the process of vaporization. So how much water do we need? Sorry, I have a little tickle in my throat. How much energy do we need to change liquid water into water vapors? And so here you can start to see these little red dots are water molecules, and these arrows are showing movement of water molecules. If you heat up this water, eventually the hydrogen bonds between the water molecules will absorb so much heat that they will break. And when they break, outshoot those water molecules in the form of water vapors. Now, this is the same beaker. If you had put a lid on it, you would trap those water molecules back in here. But let's focus on this right here. So what I want for us to know is that water has a very high heat of vaporization, which means we know that hydrogen bonds can absorb a whole lot of energy, right? We just saw that with heat or with specific heat. So they can absorb a lot of energy before they actually transition phases from a liquid to a gas. But when they do, they have absorbed so much heat, they start releasing that heat. So as water vaporizes, we get quite a bit of heat energy lost. And that can be good if we're trying to cool something down. Before we go to the next picture, I want you to visualize the vaporization process. So let's look for just a second. Let's turn these into water molecules. This is water molecules. We're not going to mess with pressure. We're not going to pressurize it. That would let us talk about some other concepts. We're just going to alter the temperature. So first, I'm going to cool the temperature down. So we're going to apply some ice to it. And notice what happens. This is a good visualization of just molecular motion when temperatures are applied. The molecules are slowing down. And eventually we learned that if it gets cold enough that it freezes, hydrogen bonds would lock themselves into place and spread out the water molecules and create a solid that's way less dense than its liquid, and ice would float. Now let's do the opposite. Eventually we froze them to a standstill. Let's do the opposite. Let's heat them up. Now this is more relevant to our vaporization conversation. So we're going to apply heat. And we're going to keep applying heat. Notice all of that kinetic energy. The molecules are spinning and spinning and spinning. And finally, they get so hot that they break their hydrogen bonds and they start to float off. So you can see these molecules that would escape if we didn't have a lid on the chamber, they would vaporize. And so what I want for you to think about and see is that as these water molecules start to spin off and disconnect and vaporize, they actually release heat energy in the bonds that are broken, and heat goes with the molecules up and away from whatever the surface was that the water was on. So this becomes, we'll let it calm down here. This becomes important in continuing a discussion on moderating temperature, right? So we know that water has a high heat of vaporization. We know that hydrogen bonds between water molecules can absorb a lot of energy, but when they do finally break free and vaporize, they release that energy with them. And so why is that important? Because that leads to something called evaporative cooling. So you might think of this as sweating. And you know that when we sweat, eventually, we cool down. So evaporative cooling is connected back to high heat of vaporization. So evaporative cooling is due to the fact that water has high heat of vaporization. So when we do sweat, and it does evaporate, it changes form. We know that that has happened because the hydrogen bonds have absorbed so much energy and then release that energy as it transitions from a liquid to a gas form, from liquid sweat to its vapor, and takes that heat energy with it away from the surface. So lots and lots and lots of heat energy will leave our skin as sweat vaporizes because water has a high heat of vaporization. It took a whole lot of energy to get us to the vaporization point, and now that it is vaporizing, our sweat is vaporizing, it's releasing a ton of energy with it. And that leaves our skin ultimately cooler. So here's a picture of that. If we were to look at, here's your skin, sweat glands embedded that are producing liquid sweat, which really is just a dilute form of urine. Let that sit for just a second, maybe gross you out. As this liquid evaporates and turns into a gas, it takes heat energy off of the skin with it. And so then we, as a result, are cooler. So the last section of our notes is related to pH. I am going to leave this for the homework that we'll talk about in class. It'll be done over the weekend and due, whether you're an A group or a B group, it'll be due the first time that you return to in-person school next week. So you'll take your pH notes over the weekend, and when we get back together in class, I will ask to see this notes packet fully filled out, and we will do a little pH buffer demonstration on day 1. So you're done.